Thank you very much, Professor Wu, for the introduction. Thanks very much, Ela, for the kind introduction, kind invitation. It's my pleasure to be here to report to you some of the stories we have been developing in the past few years using nanoelectromechanical system to do logic for energy efficiency and longevity and harsh environment. And specifically, I'm focused on talking about silicon carbide devices. And similar to the devices presented in a previous talk, we're going to be using collective mechanical motion of billions of atoms from a movable structure. Different from that one is here, most of the devices are suspended, they're free to move, and they're moving in a different mode. And here is a selected gallery of devices I have been marrying or making in the past few years. This is a metallized in-plane cantilever device. This is the much smaller one. A similar device is multi-gate coupled devices with a point contact, quantum limited point contact gate. There's a nanowire, top-down nanowire suspended next to a 15 micrometer long gate with 30 nanometer gap. And quickly introduce the place where I'm from, because the name, located in the Modest, Ohio. We do have very nicely defined 4 seasons and with a gorgeous summer. And we also have some interesting historical academic reputation before the merger from Case Institute of Technology and Western Reserve. The university actually has the first winner of Nobel Prize in Physics for the U.S. And to date, we have like 16 Nobel laureates. We have a very small student body. It's a private school with highly selected students, undergraduates especially. If you have a chance to stop by Chicago or Cleveland, just call me. I would be very happy to show you around the university.
Cleveland, right?
Yeah. So, my research group at Case Western are primarily focusing on doing a few things that are exploiting controllable mechanical degrees of freedoms in nanostructures. One topic we're actively exploring is atomically thin 2D crystals for sensing and logic devices. Other topics, NEMS-based radio frequency signal processing. And the third one is this blue sky research and based on mechanically derived steep slope devices for ultra-low power logic and computing. And today's talk is primarily focused on this one. And with the audience of such, I think this slide needs no explanation. And specifically, at the device level, we have, over the last day and a half, we have revisited this many times. Basically, today's MOSFET devices based on silicon suffer from various types of leakage current. And specifically, this is off-state drain source current, leakage current, which is also very unfriendly to device scaling. If we scale the voltage linearly, we're going to suffer from increase of off-state current exponentially. And there is a great desire of building steep slope, subthreshold slope devices. And basically, to beat this thermodynamically limited subthreshold swing, there are a few possibilities people have been actively looking. Interband tunneling has been extensively discussed here. I'm going to look into mechanical motion. So to realize concrete schemes for implementing logic using mechanical motion in micro nanostructures, people have come out pretty much two paradigms. One is to hybrid a mechanically movable structure into existing transistor, MOSFET. So this can be split into two specific approaches. One is suspended gate, so you make the gate movable. The other one, you make the channel movable. So shown here is the example pioneered by Professors Andrei Ionescu, Roger Howe, and Philip Wang, Stanford. So they proposed this suspended gate using air gap to decouple the gate when it's at off state. So you can use the mechanical motion of the gate to modulate the off-state leakage current and to achieve sharp mechanical switching. And the other approach is purely looking at nanomechanical motion. But in the nanomechanical structure, we integrate electrical conductivity. So this is the integrated nanoelectromechanical switches. The basic idea is I give two examples. Shown this one, this is a top view of SEM device of lateral dual gate, complementary gate coupled devices. You can imagine that this when we apply voltage here, this gap is going to reduce and the current from drain to source will increase following the red one. When you remove the voltage at the gate, the current is going to restore back to zero. So this is a mechanical switch, and this is the plot of gap versus voltage applied. This is the current versus gate. And you can implement this not only electrostatically, but also other mechanics like a piezoelectric cantilever, which is illustrated here, using a vertical configuration. You can achieve the similar characteristics in switching. And this is not a new idea. It's pretty much a redux of the old mechanical relay idea, which has been replaced by solid-state transistor switch. But now it's worth revisiting, actually, after many years of development in semiconductor manufacturing technology. So today we are at the point that we can make nanoelectromechanical systems with very small footprint. So that's a good thing. So we can make them smaller than the top view of a CMOS transistor. And because NEMS has this intrinsic merit, including at the off state, there is absolutely low leakage and this very high on-off ratio. And it can be very fast because we can make gigahertz vibrating devices by utilizing different modes. And mechanical structure also high temperature compatible, and their resistance to various electromagnetic radiations. And their operating power is very low, actually, usually below nanowatt or picowatt level. So if we have successfully made various of mechanical switching devices, we are thinking of integrating them into this all mechanical. So this is basically an inverter based on a pair of mechanical switch. And this is a hybrid inverter with a pair of mechanical switches power gating the existing CMOS. So this is basically a cross-section view of this scheme. Okay. So just a quick one-slide review of how to make nanoelectromechanical devices today. So usually they have feature sizes smaller than 100 nanometer, and their volume is about a million times smaller than today's MEMS device you enjoy in your portable devices like iPhone. And for two approaches, basically. For making bottom-up approach devices, we use chemical synthesis. For making a top-down, basically, we carve structures out of a wafer using a lithography and chemical etching process. So the first story I'm going to share with you are the work we have done at Caltech when this program was early. We have a team. It was supporting 2 graduate students, and also we have help from a staff scientist and a Kavli fellow, Professor Ji Xiang here. And the first generation devices we're making is based on SOI wafer, metallized devices. I show a couple of structure here. And you can see we were able to achieve a 30 nanometer gap. That's our early excitement. We were trying to achieve very small lateral coupling gaps, and with various of mechanical structures, trying to demonstrate switching event in the early days. So So this highlights the electrostatic coupling gap and switching gap. And we have all sorts of devices, and showing here a typical lateral electrostatically coupled switching device switching at a few volts. And this one is a much shorter device but switching at a higher volt. And this one switching at near 10 volt. And I want to highlight one of the smallest devices we were able to achieve back then, with a switching gap, coupling gap of 50 nanometer, switching gap of like 15 nanometer by top-down lithography. Everything here is all the movable parts and the electromechanically active part are smaller than 1 micron. And we were able to build complementary mechanical logic using this all-silicon SOI film. And the challenge, after we have made all those good-looking devices, actually a lot of the challenge stem from electromechanical characterization or measurement, low noise measurement. So we did a lot of measurement in this system showing like this, basically to do in situ measurement. And we achieve something like this. For many of the devices, we can see we have individual switching event below 5 volt, but we also have great challenge we were facing. So there are usually very limited number of cycles. In hot switching, from a few cycles to a few hundreds of cycles. In cold switching, we can, by not passing current through the contact, we do have a record of passing, making contact for hundreds of millions of times, but they're not current flowing through the contact. So the majority of today's NEMS device has been suffering this contact or lifetime issue. That's what we call the elephant in the living room. And we were looking, since the story with the metallic or metallized SOI technology and also the doped SOI technology, we were seeing some light in the tunnel. We were feeling that a doped better material might be the route to go. So we were looking into silicon carbide material. Silicon carbide material is very interesting because it's technologically important for harsh environment. It has a very long established history in high temperature electronics and also high temperature sensors and actuators. So it can operate at the temperatures that silicon is not functioning or silicon transistor is not functioning. Its resistance to high shock, to high radiation, and basically it's very hard to find a chemical edge of silicon carbide that makes it very suitable for harsh environment. And we can do very good devices also with silicon carbide. We have a long-standing history in the past decade making suspended and high-speed vibrating silicon nanowire, silicon carbide devices. And so the first generation, we still put down some metal, but we were able to demonstrate ultra-thin silicon carbide nanowire switching at low voltage. And then we built, actually with, I moved, and then we built a new team there to study this with the support from DARPA. And this is a roadmap mostly since 2010. We have produced generations of mechanical switching devices toward some degree of robustness and longevity. I will show in the following slides. And so today's data I will show mostly will be from the NEMS and MEMS conference, transducer conference. And because the limitation of the IEDM, we have a paper in December coming. So this slide shows the basic fundamental design and the simulation and calculation between the trade-offs of this type of structure. So we focus on a 3-terminal lateral electrostatically coupled mechanical switch. And this shows on each die we have different devices and different logic gates. And this shows a fabrication process, cross-section flow of the fabrication process. Basically, we have our capability to grow silicon carbide down to tens of nanometers thin on silicon oxide. So this carbide on insulator technology is the key for us to do all this work. And our fabrication is wafer-scale lithography combined with dry etch and the vapor HF release of the sacrificial oxide. And the switching behavior here, when we do a basic IV sweep of this 3-terminal electromechanical devices based on the silicon carbide cantilever, we can see that the green one shows the gate current going up and back does not change, stays at the noise floor of the instrument, while the drain current will jump abruptly, showing clear evidence of a mechanical abrupt switching. And this shows another device with clearly showing the cycle numbers, as you can see indicated by the red arrows. And the top plot, we always plot the switching characteristics like this. The top one is a current in log, and the bottom one is current in linear scale. And there's very interesting fundamental characteristic in this electromechanical 3-terminal switching devices I want to emphasize, because it's very easy to miss this, because this switching characteristic seems straightforward and easy, but actually there are subtleties. So if you look at this one, say, if we sweep the gate voltage, first the drain current is going to jump, showing a mechanical contact from the cantilever to the drain. But there's a narrow window or designed window or intentionally designed window that prohibits us from increasing the actuation voltage too high. If we increase too high, then this cantilever will also pull into the gate, and you can see that the drain current will drop, and then the gate current will increase abruptly. There's another mechanical switch to the gate. And this regime, this characteristic is unwanted, is undesired. We don't want this to happen. And this is also detrimental or destructive in testing the device. Beyond this 22 volts, this device is very hard to release. We only can have chemical method try to salvage these devices. So shown here is a time domain measurement of the switching event after the basic calibration of the calibration of the IV curve, and we drive the device using a train of using a waveform of square wave gate voltage to see the device response, and we can see the device gate current is always negligible, while the drain current follows the gate drive, so showing a time domain switching event. And this shows very interesting, again, log plot and linear plot. And when the peak voltage of the driving gate voltage waveform is above the threshold, we have this mechanical switching event. And this control experiment shows that when the gate voltage when the peak voltage of the gate waveform is below the threshold, there's no mechanical switching. So this clearly verifies this mechanical nature in this time domain measurement. And so we have done this over a long time in ambient air, actually students sitting, and we actually do shift recording the data. So this data includes 7 days of switching event without missing a single cycle. And within each cycle, if we zoom in box 1, we have all the data recorded. If we zoom in on day 7, in box 7, we have this. And at the beginning, the switching looked like this, and after that, after some time, it's degraded. After 7 days, actually, there is some degradation. If we collect the I on versus I off over the 7 days, we have a little bit degradation of it's in ambient air of the contact resistance and off ratio.
Is silicon carbide coated with metal at this point?
At this point, no.
So
it's doped.
It's just doped.
Yes. So now that was sort of a slow measurement. We want to speed up the measurement so that we can approach the intrinsic lifetime that's available. But the challenge is actually interrogating this type of switching at high speed, electrically is very hard because we have to build a circuit. So this is a circuit we build. I'm going to quickly run through this. This is the measurement setup, and this is a probe up calibration. And you can see, because we don't know what will be the contact resistance at the beginning, so we have to blindly design some circuit based on experience or based on some guessing based on the basic IV curve, but then the contact resistance in time domain interrogation may actually fluctuate. So we need to have an adaptive time domain circuit. So this is a simulation of using different bleeding resistor and different coupling capacitor, what we are expecting. The red is always voltage and the input, and the blue is always voltage output. And this is a time domain measurement over 1 million cycles recorded. And if we zoom in different regime, we actually see that just 1 minute. We actually see that the fluctuation of the contact resistance. So if we benchmark this device and with the recorded cycle of numbers versus the motional volume, we see there's interesting correlation. Actually, we are the best in nanoscale devices. We are on par with today's the state of the art high performance NEMS contact RF switches. We also have some high temperature data. Just skip those. Basically, the device you can see in ambient environment and with high temperature up to 500, and it has robust performance. The last story I want to share is interrogating switching dynamics by using a pump probe scheme, so that we can. So basically, we drive the device using a laser, and then we use a very small laser spot focusing at the contact. The goal is to be able to see what the contact is doing so that we understand better the contact's dynamics so we can better engineer it. The optics allow us to selectively operate this device in this in-plane mode and also in out-of-plane mode. So we, of course, select the in-plane mode, and we actually see that when we drive the device harder, the device is going to impacting the gate, and the displacement is automatically limited there. When you increase the drive, it no longer increases. It shows very interesting displacement limited nonlinearity. And this is the first time we show this device in AC operation in both gate voltage and actuation and bias voltage below 0.5 volt. And future, I have a movie, I'll skip it. I think one thing to do is to have time-resolved probing of switching dynamics. So this is the simulation results, but we really want to do this experimentally. Second is to integrate silicon carbide NEMS with silicon carbide electronics, which in comparison with silicon electronics are really in stone age. And very interesting other possibilities to do things using ultralight mass materials such as graphene. We actually demonstrate a switching device at 4 volt, and moly disulfide devices we were able to demonstrate electromechanical coupling recently. And with that, I want to thank my group and thank the funding agency. Thank you all very much for your attention.
So what is the secret? You have silicon carbide contacting silicon carbide. What makes that better? I mean, I think an oxide will form. That doesn't sound so good to me. So tell me what makes this better.
I think we found two things. One is the profile where the contact is made. Second is the silicon carbide compared to silicon, the oxidation is different. Yeah, we do have probably oxidation, but it's much weaker or much harder to affect the performance than in the silicon cantilever case.
And just a quick follow. In your testing, do you test relative to the total number of coulombs going through the contact? It seems that would be a fair test. Well, for example, if you have almost no current flow, of course it's going to last a long time. But if you're putting a lot of current through, then it won't last so long. So current times time is coulombs.
Yes, we have some interesting observation just to that. I'll explain to you. But we have 1 microamp on current, pretty much. So on-off ratio is usually 10 to the 6th or 10 to the 5th.
Okay, let's thank the speaker at the time.